This lesson is part 1 of section 2.7 on related rates. Our objective for today is to solve a related rates problem. So a related rates problem can really easily be identified because the question will always ask you how quickly some quantity is changing when you're given how quickly another quantity is changing. So these quantities will be related to one another. That's why they're called related rates. And you're looking for a rate of change. So how quickly some quantity is changing. Now there's a few classic types of related rates problems, and we're going to cover those today. We're going to cover the first 3. So we're going to look at a falling ladder problem, which has Pythagorean theorem applications. There are, among other problems that are similar to this, the leaky container problem, as well as the lamppost and the shadow problem. So I think in the next lesson we'll get to the change in angle problem, as well as some much more difficult examples. So just to be clear, these aren't all the different types of problems that you're going to see. These are just some of the classic types of related rates problems that you might run into. Okay, so let's talk about how related rates are really just an application of implicit differentiation. So we're going to begin by trying to differentiate the following equations here with respect to time. So we're going to find the derivative with respect to time for each of these equations. So let's take a look at our first example. We have the equation a equals s squared. So you may recognize that this is just the formula for the area of a square, because if s is a length of the side of a square, then you would just square that value to get its area. And we'll talk about that in terms of a rate and a related rate in just a moment, but let's first talk about how we would find the derivative of this equation with respect to time. So it seems a bit odd at first for students because we're not really going to differentiate a with respect to s or even differentiate s with respect to a. We're differentiating both variables here with respect to time. So the derivative of a with respect to time is dA dt. Easy enough. And the derivative of s squared with respect to time, that's going to be 2s times ds dt. So earlier I mentioned that this equation here is just the area for a square, right? Now when you take the derivative of that equation, you're introducing related rates. So these are two different rates here, rates of change that are related to one another through this equation. Now this represents the rate of change of the area of the square, while this rate here represents the rate of change of a side length of that square. So these two rates we would call related rates because they're related to one another in an equation. Now moving on to example B, if we want to find the derivative of this equation with respect to time, we're going to look at each piece here and find the derivative of each with respect to time. So we have the derivative of x squared with respect to time will be 2x times dx dt. Okay. The derivative of y squared with respect to time will be 2y times dy dt, and you're probably catching on that the derivative of d squared with respect to time will be 2d times dd dt. And in our final example here, if we want to differentiate this equation with respect to time, we're going to have to use the product rule because we do have a product on the right-hand side. Now pi is not a variable, so you only have two variables, r and h. Let's group 2 pi r together, call that one function, and h a different function. So we're going to definitely have to use f times g prime plus f prime times g, the product rule here, to differentiate the right-hand side. Now the derivative of s with respect to t is just ds dt. And on the right-hand side, to differentiate 2 pi rh with respect to time, that's going to become 2 pi r times the derivative of h, which is just dh dt, plus the derivative now of 2 pi r, which is 2 pi times dr dt. And then multiply that by h. So here is the derivative of that equation with respect to time. So here we have 3 different rates that are all related to one another. All right, in problem D, we're looking at an actual related rates problem. They ask us to find a specific rate, dA dt, when b is equal to 1 and c is equal to 2, when we have an equation here that relates all of our variables, a, b, and c, as well as a couple different given rates. So if we want to find this rate of change here, what we're going to have to do is come over to this original equation that relates those variables and differentiate it so that we can find how our rates are related to one another. Get it? Related rates. Okay. So we differentiate here with respect to time. So we have 2a times dA dt equals 2b times dB dt plus 4 times dB dt plus 2c times dC dt. So our goal is to isolate dA dt and find dA dt. So I'm going to divide now by 2a. Okay, so let's get rid of this over here. And because I have that common factor here, let's see, that becomes a 2 now. That becomes 1. So let's go ahead and erase so I don't have to rewrite everything. So that was a 2. All right, so we've got dA dt isolated. Now, to find dA dt, we have every single one of these values in the numerator given to us already. We're just missing a. All right, so how would we go about finding a? Well, this is where you have to come back to your original equation here, because that original equation relates the variables a, b, and c. So we can actually solve for a here. One of the things I forgot to type up is that you're going to assume a is positive. Okay, so when we solve for a here, we have a squared is equal to, just by substituting, 1 squared plus 4 times 1 plus 2 squared. So we have a squared is equal to 9, and because we're assuming that a is positive, we're going to go with a is equal to 3. So now we can go ahead and actually plug in all those values into this equation to evaluate dA dt. So I'll go ahead and pause so we can do that. So after making the appropriate substitutions, we have 12 in the numerator divided by 3. So we have dA dt is equal to 4. All right, so let's work on our first related rates word problem. This is the falling ladder problem, okay? So it says a ladder is sliding down a vertical wall. If the ladder is 10 meters long and the top is slipping at the constant rate of 10 meters per second, how fast is the bottom of the ladder moving along the ground when the bottom is 6 meters from the wall? So you're probably noticing that this question is a lot more difficult than the example above, and the reason why is because here we're not given an equation, so it's not just a matter of, differentiation and then evaluating something. Here we actually have to do a lot of thinking to figure out what's going on in the problem. Now, to help you to solve these related rates problems, there is an acronym that I find useful. It's the acronym DREADS. So the first D in DREADS stands for diagram, okay? Now, typically, the variables in your word problem will somehow have a geometric relationship to one another. So drawing a diagram is the best way to understand what's going on in the problem. So you want to do that first. So after you have that diagram, next you're going to be looking for your known quantities and your unknown quantities. So what you want to determine are the rates that you're given and the rates that you're asked to find. So once you have those quantities, once you've found those pieces of information, make sure you go back to your diagram and label the parts appropriately. Now at this point you should be ready to write an equation that relates your variables. So sometimes you'll have to combine 2 or more equations into one, but you want to make sure that your equation matches what's going on in your diagram. Next, you're going to differentiate that equation with respect to time so that you can create a relationship between those rates. And then for your final step, you're going to substitute in your known values into the equation. So I can't stress this enough. This should be the last thing that you ever do. Because a lot of times when students make mistakes, it's because they've substituted quantities into the equation way too early. So make sure it's the last thing that you're going to do here. Okay? All right, so let's get started on this problem with drawing our diagram. So this diagram is pretty straightforward. We have a vertical wall and leaning up against it is a ladder here. Okay, so we're definitely dealing with a right triangle. Now there's some parts in this diagram that I'm going to go ahead and label. For example, the hypotenuse here is going to be a constant 10 meters. This is not a variable, this is a constant, and it'll never change because the length of your ladder can't change. There are some variables here though, because let's call this x since it's horizontal here, and we'll call this y. These two values will change. As that ladder slips here, y will decrease and x will increase. Okay, so we're done with our diagram, and let's move on now to the rates. So they tell us that the top of the ladder is slipping at a constant rate of 10 meters per second. So what I'm going to do is label over here on the side of the diagram dy dt, so the rate of change of y, that's negative 10 meters per second. So we're specifically asked to find how fast the bottom of the ladder is moving along the ground when the bottom is 6 meters from the wall. Okay, so what we're looking to find is dx dt, that's the rate we're looking for, when x is equal to 6. Okay, so please make sure you are labeling appropriately in your diagram. All right, so now that we've gone through and found all of the important information and placed it into our diagram, we're ready to write our equation. So if we look at our diagram, I can relate the variables x and y with Pythagorean theorem. X squared plus y squared should equal 10 squared. All right, now we've got our equation. Now let's go ahead and differentiate this equation here with respect to time. So we have 2x times dx dt plus 2y times dy dt equals just 0. Now our goal is to find dx dt, right? So what I'm going to do is isolate dx dt. So I would move over that 2y dy dt term, so it becomes negative. And then I'd have to divide out that 2x. So if I just reduce here, I'm looking at negative y times dy dt all over x. So now what I'm going to have to do is my very last step, and that's to substitute in values into this particular equation. All right, so again, we have dy dt, right? We already know this value. That's negative 10 meters per second. We have x, that value is supposed to be at 6, right? At 6 meters from the wall. The only thing we're missing is y. And here's where students get stuck, or they pick an inappropriate value for this. You have to make sure that you go back to your original equation, just like we did in the problem above, and you're going to substitute in the known value here because that allows you to solve for y. So this is the only equation where you're able to actually solve for a missing unknown. So you have to plug it into here. So we have 6 squared plus y squared equals 10 squared. So that's a Pythagorean triple. We get y is equal to 8. So now we can go ahead and evaluate dx dt by plugging in 8 for y. So if we go ahead and substitute, dx dt should equal negative 8 meters times negative 10 meters per second, all over 6 meters. Now, I don't typically write in the units every single time I do a related rates problem, but I think because it's the first time we're doing a question together, it's important to show you that the units here do really matter, and also it's a great way to check your final answer. So your units here should end up being meters per second. So if we just go through here, we end up with positive 80 meters squared per second divided by 6 meters, and obviously those your units here can cancel as well, so we end up with 40 meters per second. So we definitely have a reasonable answer here because our units check off. All right, so let's move on to our next example. Here it says a spherical balloon was filled with 4,500 pi cubic inches of helium. A leak in the balloon caused the helium to escape at a rate of 72 pi cubic inches per minute. At what rate was the radius of the balloon decreasing 49 minutes after the leak began? So let's start with our diagram here. We have a sphere, and we're talking about the volume of this sphere. Okay, it's leaking gas, which means it's shrinking. Okay, the overall sphere is shrinking, and your volume will shrink as well. So let's label this as R. Now, there's a couple pieces of information here. It says a spherical balloon was filled with 4,500 pi cubic inches of helium. So that's when time is 0. So at t equals 0, you have a volume of 4,500 pi. Okay. Now, the leak lets out gas at a rate of 72 pi cubic inches per minute. That's the change in your volume. So dV dt, this is negative 72 pi. And that's cubic inches per minute. So this question asks, at what rate was the radius of the balloon decreasing 49 minutes after the leak began? So if we're asking for the rate of the radius decreasing, that means we're looking for dr dt. Okay, so that's what we're missing, dr dt. All right, so we have our information all written into our diagram, so now we should be ready for our equation. There is one more piece of information, though, I'm just going to kind of write underneath here. We're looking at the rate of change of that radius after 49 minutes. Okay, that's a very important piece of information. We'll talk about that in a little bit. So for our equation here, let's use the volume of a sphere, 4/3 pi r cubed. No, you do not have to have these memorized, but it would help you if you were, working on your homework to go a little bit quicker if you don't have to look up all of these formulas. But we'll provide you with the formulas on your quiz, so don't worry about that. All right, so we've got our equation. Now we're going to differentiate this equation here with respect to time. All right, so the derivative of v with respect to time is going to be dv dt. And on the right-hand side, you only have one variable here, so it's not a product, no need for a product rule. You're just going to take that power and multiply it out in front. So you have 4/3 times 3. That leaves you with 4 pi, then r squared. Then, of course, you have to make sure you multiply by dr dt. So remember, we're trying to solve for dr dt, so we can go ahead and isolate that now. So dr dt is going to be dv dt divided by 4 pi r squared. All right, so to find dr dt here, we need to know r. That's still a missing value for us. And again, to find that missing value, you're going to go back to your original equation that relates your variables. Okay, so in this case, if we're solving for r, if we want to find r, that means we should know v. But in this case, we actually don't know v at the specific time that we're looking at. We want to know after 49 minutes of that leak what your volume is. You only know what your volume is to start, right? At time of 0, you have 4,500 pi cubic inches of helium in there. But after 49 minutes, how much volume would be left? All right, so in order to find this volume here, which will then lead to the radius at that specific time frame, we're going to have to do a little bit of work. So for the volume at 49 minutes, what we're going to have to first figure out is how much has leaked at that point. So for 49 minutes straight, the sphere is leaking at a constant rate of 72 pi cubic inches per minute. Okay, so that's a total of, let's see, 3,528 pi cubic inches of volume that has been leaked. All right, so to find my volume at that specific time, I'm just going to take 4,500 pi and subtract 352.8 pi to end up with 972 pi cubic inches of helium. Okay, that's the volume right now at 49 minutes. All right, so finding that volume now allows me to use this equation here to solve for R. Remember, we need R in order to find dr dt. So if we take 972 pi and we set it equal to 4/3 pi r cubed, we'll be able to solve for R. All right, so if we multiply by 3/4 and divide by pi, we're going to end up with r cubed equals 729. Now, if we solve for R, we end up with R equals 9. So here's our radius, okay, at 49 minutes. Now we can go ahead and plug that value into this equation here so that we can finally get dr dt. All right, so after we make those substitutions, let's go ahead and try to simplify this. Now, negative 72 over 4, that's going to be negative 18, and the pi's will cancel. So I have negative 18 cubic inches per minute over, now 9 inches, that quantity squared, that's going to give me 81 square inches. Okay, and what's nice about these units here, one more time, I can check to make sure that this should give me inches per minute because the radius is a linear change, right? So we should have inches per your time frame, which is in minutes. So this does make sense. These will cancel here and leave you with inches per minute, so that's good. And then negative 18 over 81, we can simplify that, and that's negative 2/9. So the rate at which your radius is changing at 49 minutes is negative 2/9 inches per minute. All right, for our final example here, we're going to look at the lamppost and shadow problem. Here it says a man 6 feet tall walks at a rate of 2 feet per second away from an 18-foot lamppost. When he is 12 feet away from the base of the light, we're going to go ahead and answer two separate questions. At what rate is the length of his shadow changing, and at what rate is the point at the end of his shadow moving? All right, so let's go ahead and start with our diagram. So we have a lamppost. So let's go ahead and draw in our lamppost here. Now I'm going to label that 18, right? It says 18 feet because that quantity isn't going to change. And I have a man standing away from that lamppost. Okay, so here's our 6-foot tall guy. And we're looking at his shadow. So we're casting a shadow because the light here from that lamppost will hit his head and cause this shadow. So here's where his shadow is going to occur. All right, so we're really dealing with, let me erase the guy and just draw in a segment here. We're really dealing with some similar triangles. Okay, this is not a Pythagorean theorem, even though we do have right triangles. We're actually dealing with similar right triangles. So I'm going to go ahead and start labeling some of these variables. So I do know that the distance he is away from the lamppost is going to change, and I'm going to call that distance here x. And then I know that the length of his shadow is also supposed to be changing, so I'm going to call that s. Okay. Now, based off of this, I can also start writing in some rates of change. It says he's walking away from the lamppost at a rate of 2 feet per second. Okay, so that means dx dt. This is equal to 2, and I'm going to write feet per second. I'm being a stickler about all the units right now. Okay, now when he is 12 feet away from the base of the light, so at x equals 12, okay, we want to know how the rate of his, the length of his shadow is changing. So we want to know ds dt at that specific time. All right, so now that we've put our information into that diagram, let's go ahead and try to come up with an equation that will relate our variables. So as I mentioned, these are similar right triangles, so we have some relationships between the sides of the triangle. So using proportions, we know that s over s plus x, that's going to equal 6 over 18. Now if I wanted to go ahead and just differentiate this, I could, but I'm going to deal with a quotient on the left-hand side, and I can change this form really easily by just cross-multiplying. So I have 18s equals 6s plus 6x. And if I just subtract that 6s over, I have 12s equals 6x. So this is an equation that will still relate my two variables, okay? And it's much easier to differentiate than our original equation. All right, now if we go ahead and differentiate this equation here with respect to time, we're going to have 12 times ds dt equals 6 times dx dt. So let's go ahead and isolate ds dt because that's after all what we're trying to find. So ds dt is going to equal 6 divided by 12, which is going to give me 1/2 times dx dt. So if we want to evaluate ds dt, all we'll have to do then is plug in dx dt, which we already know. So ds dt is equal to 1/2 times 2 feet per second. Okay, so we end up with 1 foot per second, and that's the rate of change for the length of his shadow. So this particular problem is pretty unique because we never had to find another unknown value. Remember, in the last couple problems, once we tried to evaluate our rate, we had to find some missing information still. In this case, we didn't have to do that. And actually, nothing really was dependent on the fact that he was 12, oops, I forgot the 12, the one. Nothing was dependent on the fact that he was 12 feet away from the lamppost. So this rate of change is constant. It doesn't matter if he's 3 feet away from the lamppost or 70 feet away from the lamppost. The length of his shadow will change at that same constant rate. All right, now in part B, it asks at what rate is the point at the end of his shadow moving? Okay, so if this is the point at the end of his shadow, we're really looking at this entire length here and asking how that length changes. So let's call that L. Okay, and let me go ahead and pause so I can erase here and make some more room for this part B. Okay, so in this problem here, we are trying to find dl dt. That's the rate we're looking at. Okay, we don't know dl dt. We still need to use the fact that dx dt is 2 feet per second. Okay, and we might need to know that x is equal to 12 feet. Let's see if we do though. Okay, now if we're going to relate using our diagram here, our variables, well, it's really simple here. L is equal to x plus s, right? We don't even need to use any similar triangles here. L is equal to x plus s. Now, if we differentiate this equation here, that gives me dl dt, okay? And over on the other side, this is dx dt plus ds dt. All right, so we can find dl dt by substituting in dx and ds dt, which is what we just found. So dl dt is equal to 2 feet per second plus that 1 foot per second. And because these have the exact same units, we are able to add them together, so we get 3 feet per second. Okay, so this is dl dt. That's the rate at which the point at the end of his shadow is moving. Now, we can also use an alternative method here. So let me go back up to this original equation that we found, L is equal to x plus s. So let's try to rewrite this side here in terms of just one variable as opposed to two, because there is a relationship between s and x, right? We found that before in our original equation here. If I solve for s and I divide the 12 here, I end up with 1/2 x. So if I go ahead and make that substitution here for s, now I'm looking at L is equal to x plus 1/2 x, or 3/2 x, okay? So if I go ahead and I differentiate this equation, now I have dl dt is equal to 3/2 times dx dt. And then if I go ahead and evaluate dl dt by substituting in dx dt, we have 3/2 times 2 feet per second. So we do end up again with 3 feet per second. So either way, whichever equation we use, we end up with that exact same rate for the point at the end of his shadow. All right, guys, so that is the end of the lesson. These related rates can be really tricky. Setting up the equation is definitely the hardest part. So the best way to prepare yourself for a quiz on this is to get as much practice seeing as many types of problems as you can. So make sure that you're in class working hard and asking questions when you run into trouble. All right, nice job. I will see you guys in class tomorrow.